All right. Technology. Thank you guys for having me. Thank you for the very nice introduction, and thank you all for coming to hear me talk. I hope that you get something out of it. That's sort of the point of all of this, right? So my name is Brandon Harris. I work at Electric Imp. I studied computer engineering at Washington University in St. Louis, where I worked on how do we describe FPGA-based biosequencing search tools, which basically meant taking existing software, jamming it down into hardware, and making it run 100 times faster. I've worked at chip companies, Apple, where I worked on phones and tablets, Google, I was working on laptops, and now Electric Imp. I run the hardware team as well as the customer support engineering team. So through a little more about Electric Imp tonight. Electric Imp is basically a cloud solutions provider for the IoT. That means we do some hardware and an awful lot of software. We have the in-cloud, which is basically a way for you to interact with your devices online. ImpOS, which runs on the local hardware, makes developing your applications nice and easy. ClickUp is a technology we use for configuring Wi-Fi. And then we also help you scale and provide some FCC certified hardware. So I don't want tonight to be, all marketing, and I apologize for that previous slide. That's not why I'm here. I'm here because I'm an engineer and I like talking about engineering. As part of that, I'm a very collaborative learner. I encourage you guys at any point tonight during the talk, just throw up your hand, ask some questions, give me feedback, shouts of agreement, hopefully not too many boos, but if you disagree with me, feel free to let me know. And provide feedback, right? This is meant to be about you guys learning, and that doesn't work if I just stand here and talk and don't hear me. So tonight I'm going to be talking about 4 different wireless communication protocols: cellular, Wi-Fi, Bluetooth, and Z-Wave. There are enough different wireless protocols to fill an entire encyclopedia. So why I think those 4 is because those are the 4 that I know best. There are lots of new ones that are coming out every day. Intel, Samsung all announced their own new application layers. So I'm even going to have to narrow it down more than just talking about those 4, because any one of them could be multiple hour-long sessions of information. So I'm specifically going to be talking about some of the hardware, or really sort of about how they fit inside of a product and how they fit inside of the Internet of Things.
So of those, only cellular is licensed, is that correct?
Yes, all of the other ones are run in DI, in unlicensed radio units. And there are some pros and cons of that, which we'll cover tonight. So I'm going to be talking, for all my examples, sort of specifically about when we start talking about cost, pre-FCC certified modules. These are what is very common in many devices today. If you don't have a radio lab, you don't want to spend $20,000 doing FCC licensing, pre-certified modules is a great way to go. RF layout can be a significant challenge for a lot of companies, so that's what we see mostly being adopted is those modules. Electric Imp is a Wi-Fi platform currently, but as I said, it's really actually about the software. Tonight, I'm not going to be talking about the Electric Imp platforms in particular. When I talk about Wi-Fi, I mean any old Wi-Fi solution. There are a couple places where I'll distinguish between the 2. But really, I want to be talking about sort of in general and not make this a argument. So comparing fruit. You're probably all wondering why you're staring at a picture of an apple, a pear, a peach, and an orange. Comparing wireless protocols is inherently challenging. It's not, does this one use more power than this one? Or is this one better than that In the same way that comparing an apple to an orange is very challenging. I love an apple pie. I think an orange pie sounds really gross. But I really like orange juice for breakfast. So they all have their own place. And so, it's impossible just to give an apples to apples comparison. Each of these are such broad categories, and even the variation between them, and between individual suppliers of modules and things like that is extremely varied. So, all of this is basically my way of excusing the fact that some of the things I say and talk about are going to be slightly imprecise, because I'm making generalizations. I'm going to tell you that all apples are green. We all know all apples aren't green, but there are enough green apples for me to make some of those generalizations. And in some cases, if you disagree with me, drop your hand and by that feedback, everyone will get some education. And I'll try and sort of provide some context for when I'm making a generalization like that and when I'm being very specific. Is everyone on board with this? All right. So, just like I somewhat arbitrarily different standards to compare, I've also picked a couple categories. So I'm going to be talking about sort of different radio topologies. This is how these devices connect to the internet. Everything is going to be geared towards building a device, whether it's a sensor node or an actuator node or something like that in some way gets the data somewhere to a internet accessible location. I'm going to talk about range. That's a very local thing. Cost, extremely subjective. Security, we'll get into that. Power consumption, complexity of implementation. You guys can all read, so I'm not going to read the rest of them. But basically, we're going to go through each of these categories, break it down. In the same way that, this is how you would talk about fruit, right? You can compare the texture of an apple to the texture of an orange, and that may be meaningful rather than trying to say, I prefer apples to oranges.
Question.
Yes?
You have 10 things. Can you pick up top 3 for a consumer point of view?
For consumer products, I think cost, power, and customer recognition are going to be the 3 most important. When somebody's in a store, knowing, identifying with your product and understanding that it will work for them is extremely important. So customer recognition is very important. Power ends up driving a lot of power stories and how many batteries does it have, how big is the device. That creates very different kinds of user experiences. A device that runs from a point cell versus a device that runs from 4 AA's are very different things. I'm not carrying 4 AA's in my pocket or on my keychain. So those would sort of be my 3 big ones. Any other questions on this?
Just you're assuming a common software stack on top of all this.
Yes. So the question was, I'm assuming the common software stack. To some degree, yeah. And that's, I'll talk a little bit about that in the topology about how data actually gets to somewhere. But yeah, that's another place where they differ greatly. All right, so topology. You guys are probably all familiar with Wi-Fi. You have a Wi-Fi router in your house, your Wi-Fi devices connect to that. In this case, we've shown a laptop because everyone associates Wi-Fi with laptops. But in this age, that can be anything. The electric connect community have powered toys, a hockey light, egg trays, power strips, wall switches, lots of things. Z-Wave, typically you have a hub, and really there should be a lot more Z-Wave devices down here, but if we're looking at a single device, it's almost always a single device to a hub, and then the hub connects into your home network, typically with a wired connection, and then to the internet from there.
So in terms of topology and interconnection, you're confining tonight's talk to single hop devices, not mesh devices?
Well, so to some degree, so Z-Wave is a mesh topology. At the end of the day, when you want to control your lights from your smartphone, you don't actually care that there might be 4 light bulbs between your hub and your light bulb. You just want the message to get there. So it's also in practice. Mesh is not used that often. Something that's phenomenal to do graduate research on. And I apologize to anybody out there who loves mesh networking. But in my experiences, I did research in it myself. It was fantastic, but it's very challenging to do. And there are very few applications where a just central hub doesn't do just as well.
Is Z-Wave Zigbee?
No, so there are, and I should point this out. So Z-Wave is a particular PHY and application layer standard. There, in addition to Z-Wave, there's also Zigbee. Then there's XP, which is built on top of Zigbee. Samsung have recently announced Thread. I can't remember what Intel called. There are a lot of different systems that look like this. 6LoWPAN is starting to be very popular. And I apologize for not being able to talk about those. It's just because I'm not up to date enough. You know, that's how it seems to go in engineering. Do you have another question back there? So Z-Wave is typically in the 868 megahertz. No, sorry, in the 900. It can also run in 2.4. So a lot of these run in the 2.4 spectrum, just because it's a high throughput, 2.4 gigahertz. It's a high throughput spectrum. So on that side, your left, we got cell phones. Again, this is how we traditionally approach cellular technology. Yeah.
Is it Wi-Fi?
What? No. So Z-Wave is separate from Wi-Fi. It's a mesh network, peer-to-peer, but it's a fixed mesh network. It doesn't have any of the self-healing so basically you set it up and it determines a route through the mesh, and then all messages are routed the same way.
I'm not sure, but I think Wi-Fi also has.
So Wi-Fi, there's an upcoming standard 802.11ah, I think. Don't have the internet in front of me, but that adds mesh networking and peer-to-peer into Wi-Fi, and that's something that I think will be very interesting because it's built on an existing platform that people are already very familiar with. Sorry.
Which body defines Z-Wave?
So Z-Wave is its own alliance, just like Bluetooth.
So one of the things you need to consider is like worldwide homologation. So I was dealing with the Census Z-Wave ICs 4 years back, and you said what, 860?
Yeah, so that's, I should have said that. Yeah, you're right. US and Europe have different bands. That's one of
two flavors.
Yeah, that's another one of the great advantages of 2.4 gigahertz is it is a worldwide unlicensed band. That's mostly because it's the same frequency that microwaves run at, and since everywhere in the world wants microwaves, and they emit ungodly amounts of RF, they have special rules at the FCC just for microwaves. That basically, you know, and that's why Wi-Fi tends to go away when you turn your microwave on if you've ever had it. Microwave close enough to your router.
It's a frequency together.
Yeah, it's getting worse. That's one of the biggest drawbacks. So cellular down there. We generally think about cellular in terms of phones. We're starting to see it, you know, as cost comes down. You know, it used to be that cellular chipsets were phenomenally expensive, you know, hundreds of dollars. Obviously, you know, the mass world adoption of cell phones is just driving the technology to the floor. That means that for non-cell phone devices, I mean, you know, your average cell phone still runs $600. The cost of the actual access is coming way down. Obviously, the biggest difference for cellular is that it runs in licensed bands. You end up paying a carrier. One of the advantages of these is that typically you've already paid Comcast for your internet, and your control signals are just piggybacking on top of that. And then Bluetooth 4.0, I apologize, I'm going to use the 4.0 notation tonight, even though it's technically incorrect. 4.0 includes all of the Bluetooth spec, but we couldn't come up with a nice logo for Bluetooth Smart or Bluetooth Elite. So I'm just going to use the 4.0 and admit that I'm wrong. But basically, this is specifically the low energy portions of Bluetooth. So it is physically incompatible with the traditional Bluetooth that you have in your car, your headset, or any of your older Bluetooth devices. It has a much simpler encoding scheme. It makes, and the medium access is much lower duty cycle. So it's phenomenal for devices that need to very occasionally do something. And this is what we're, pretty much every fitness tracker or iPhone accessory or anything else that's wireless is going to be based on the Bluetooth Smart Standard. Yes?
So I guess we understand that pointing out there's Bluetooth 4.0, there's two types, right? Two types of chips. So you're right, one of the chips is just the BLE low energy chip, exactly what you just said. Yeah. But the other 4.0 chip actually is backward compatible as well.
Yeah. So there are devices that do sort of the traditional Bluetooth, which is mostly audio. That's one of the main applications. If you're doing audio, you're probably talking about traditional Bluetooth. If you're doing small amounts of data transfer, you're probably talking about Bluetooth Smart. Are there any questions on this slide? Cool. Range. So this is where we're going to start getting into things that are much more subjective. And you'll notice I didn't put any numbers on these. The important thing here is to understand the relative differences between things. The same way that I'm not going to tell you, I'm not going to give you an absolute color for an Apple. I'm not going to tell you the absolute range of Bluetooth. In general, Bluetooth devices have a very short range. I've played with chips that are down to 10 meters of like maybe 10 meters. And it depends a lot on the environment, things like that. And actually, many of them, when you're talking about using Bluetooth for location, they'll actually intentionally back off the power to get hyper-localized. So it really is sort of all the way down at the low end of the spectrum. And they generally have chosen to optimize for power rather than for range. And again, this will sort of come back to the idea that most Bluetooth devices are designed to connect to your phone, and your phone is generally close to those devices. Z-Wave, the range goes up a little bit. Some of this is just simply because it runs at a lower frequency in the spectrum. So same output power gets you more range. Wi-Fi, there are some devices that are still comparatively low range on Wi-Fi, and obviously without doing insane things like obviously people go out to the Nevada desert and they point giant satellite dishes at each other and they get the signals to go track the curvature of the earth and stuff. And you can go tens of miles that way, but in real actual practice, with a good router, we got 800 meters on it, which surprised me. But really one of the things is that the newer standards with MIMO are doing a lot to decrease the noise floor and really improve the range, because that's one of the major complaints from customers.
Is that with stock antennas?
That was with stock antennas.
Inbuilt or external?
What's that? So it was an external antenna on the router, big 3x3 MIMO. So I mean, again, this is a high-end router, but certainly it's something that we're seeing more and more. I mean, certainly an Airport Extreme and things like that Apple's putting out are designed for high range because people want one router to cover their whole house.
Yeah, that's actually standard. So 40 dBm, which is what you're talking about, 10 watts. That's about a mile, and that's standard for most MIMO.
Yeah. So with something MIMO, we did the same test with the cheapest router we could buy, which I think was $15 at Fry's, with one little stubby antenna out the back, and we dropped in the exact same test situation. We dropped from 800 meters to 250 meters.
So it's still pretty good.
So doesn't the SEC limit output power to 1 watt in typical sort of home router Wi-Fi application?
Yeah, so there are a lot of rules on the FCC that limit your radiated power, and especially for like body-worn devices, cell phones, things like that, all have to go through SAR testing. Your body is exceedingly good at absorbing 2.4 gigahertz. Not surprisingly, again, this is the same frequency that microwaves run at. Your body's pretty filled with water. So they limit the total output power. All of these numbers are without any directional antennas and all within the FCC limits.
Yes, the FCC limit is 20 dBm. Yeah. That's the US FCC. So 36 dBm, you get 3 dBm of gain.
Yeah, and most of the stuff, you know, I mean, most embedded devices, IoT devices, are nowhere near that kind of output power. You know, they're using integrated PAs and things like that. So the input output's at a maximum of 17.5 dB. And then cellular, I don't think anybody here has questions about cellular range. It's the best in town. It will always be the best in town. This is what happens when you get your own spectrum. You just can't compete with it. And really the other ones should have been pushed more to the left. This is not properly. Yeah, we'll just call it log scale. Yeah. Yeah, it's hard to compete on that. Are there any questions about range? Cost, another really subjective one. So one of the biggest challenges with these is, of course, what are you costing, right? Is it just the Wi-Fi chip? Well, if it requires a processor to actually run it, then that's not really a fair comparison. So again, for all of these, I picked sort of either total BOM cost or integrated modules. The cost of Bluetooth has been falling precipitously. I looked a year ago, and the chips we were looking at were about $450. We're now getting quotes for fully hosted with a built-in processor. We're now getting quotes under $1. By the time you add up crystals, antenna, FCC certs, you're looking close to $2.
And what quantity are these costs?
So 100K. So large enough quantities for if you're thinking about manufacturing a product and going through radio approvals and stuff. Yeah.
So what can I buy with Z-Wave and products today?
So Z-Wave is heavy in the home automation sector, and there are a couple companies who have done branded Z-Wave. It's actually more Home Depot carries a lot of it, and so a lot of their Home Depot and then Lowe's has the Iris system, which is compatible with some Z-Wave manufacturers.
Like printer controllers, whatever. But not routers,
No. So you typically buy, with Z-Wave, you're typically buying a starter package and then adding things onto that. And so you might go and it's common, the basic home automation stuff where you get a hub and 4 light switches and 4 outlets. And one of the outlets will be controlled, and one of the outlets will be on all the time. And so those are on the market today. Those have been on the market for quite a while. Z-Wave is a relatively mature technology.
All the hubs on these have backhaul ports.
So most of the hubs do connect to your router. Only a few of them actually have web presences because, for example, Insteon rolled out a solution that did that, but they're not so hot at security. So by default, they took your setup, they piped it up to a web page. You could go to insteon.com/myusername/controls and see all of your devices. And then they didn't password protect it. And then they didn't make it put in the robots file. And so Google crawled it, which meant you could search for it. And people's homes were showing up in search results. So with the Z-Wave stuff, a number of that was not a Z-Wave product, but a lot of these traditionally hardware companies are trying to get into software, and they face a lot of challenges. Security, not the least among them. Yeah.
Okay, so 2 questions. First of all, you're talking about the average cost of a radio module.
Yes. So this is not a product.
Yeah. Okay. Second question is, I listened to some teachers at MIT Labs a month ago who was talking about Wi-Fi costing $2 to $3. Is he talking about your kind of
Yeah.
Question is, something like Qualcomm's cellular chips include built-in Wi-Fi. So you're talking about a standalone cellular chip without any of these other communication modules.
Yeah, so let's take the recording. I'll try to repeat the questions and correct me if I'm wrong. You've had people tell you Wi-Fi is getting down into the $3 range, and cellular often includes Wi-Fi, and sort of where do they come up with this $30 number? Does that include integrated Wi-Fi? So to answer the first one, Wi-Fi, it is possible to get Wi-Fi for $3. And that is, you can get something that you can plug into another computer, and it will give that computer Wi-Fi. But you still have to pay for that other computer. What I'm looking at here is sort of a fully hosted solution. So this is something that you can plug down and be done, right? So Broadcom has their Wicked platform. It integrates an STM32 microcontroller. That's several dollars. So you're adding that to the cost of your Wi-Fi. And it's pretty easy. You say, okay, well, I need to add an antenna, some crystals, a $4 processor, and my $3 worth of Wi-Fi chip, and you're at $8.
Just for clarity, so you talk about GN or AC or what are you talking about?
So mostly BGN. There are some B-only modules available on the market. They have not sold well because they don't work in some people's homes, which is the whole point of Wi-Fi.
Also work in performance with it.
Yes. So those have been relatively unpopular. BGN is exceedingly popular. AC has almost no adoption in the IoT space because there are no devices as yet that need anywhere near the performance. Even the N performance. The Wicked platform, which is one of the more popular, doesn't do bonded channels, so you're still at half the data rate on N. Most of these are oriented towards keeping it simple and not towards performance. Yeah.
So at $8, would that be enough smarts to put into, let's say, a surveillance camera, which is self-contained IP address, I can actually hop onto it?
So probably not a camera. Cameras are in particular, it's one of the hardest embedded solutions because you're dealing with video. But you know, if you wanted to do a Wi-Fi light switch or light bulb or even relatively complex things, I mean, you know, we have our third generation modules is coming down to this price. Microphone. So we have a really simple sort of, you know, it can record some audio, it can play back some audio, stuff like that. But generally, sort of in the space of IoT, cameras are not part of that. They're mostly running Linux inside of them and are much more expensive.
Yeah, so I understand your point. Actually, you get Wi-Fi for about $1.50 to $2. That's most out of China. For a video, OmniVision sells video Wi-Fi about $3. One thing I want to point out is Electric Imp is my competitor. My data Y2Y. We make the same exact product that Electric Imp does, which is Electric Imp is great. We're losing at them all the time. They're way cheaper than we are. We're much more expensive. The problem that you're trying to point out is when you talk about $1 and $2, you're talking about just the check, right? So you got the check, and you get no support for it, and you get nothing else. So people see that number of $1 to $2, and they come to Electric Imp and they go, well, I see I can buy it in China for $2. Why is it you guys are selling it for $10 or $9? Electric Imp has to go through, oh, you're doing this. They go, oh, that's what you're doing. Right? The same thing with OmniVision. You can buy the OmniVision chip, the video, to Wi-Fi, but that's all it does. It's just that. It doesn't do anything else. You want to do anything else, you got to buy something else. So it's as I'm sure you're explaining very well, it's very complicated.
Yeah. So I mean, a lot of these, it's a question of what it takes in addition to the thing you have to make a product. And really, sort of Wi-Fi $8 is about the cheapest you are going to get. Like, if you wanted to build a light switch and the mechanical parts cost you $0, and the power supply costs you $0, your cost is going to be about $8. There's a question here.
Does your Wi-Fi has beamforming?
So typically, beamforming is reserved for higher end devices. You have to have multiple antennas, which is just, and they have to be physically separated. So very few IoT devices need the performance.
Range.
It could extend the range. It's generally not worth the power, size, and cost trade-off. There are a lot of other ways to extend the range. Most of the time when we talk about extending the range, we recommend putting in higher performance routers because that extends the range of your entire network rather than a single device. And because the link is symmetric, if you improve your router, the performance of your embedded device also improves.
But that only holds for N. For AC, N could be asymmetric.
Yeah.
So for cellular, assuming you're talking with $30 for like 2G or 3G models.
Yeah, so again, the cellular is generally not geared towards performance, it's geared towards low cost. And so in the US, 2G modules are going out of style because all the carriers are trying to turn off 2G in Europe and other parts of the world because they have an embedded ecosystem. The carriers have to keep them on until 2027 or something insane. So they'll still have 2G networks for those devices to connect to, but almost everything is moving towards 3G. And in the US, it looks like 3G will have long-term support. And again, I don't need LTE on my, light switch or my data logger. There's not enough data. It's not worth the cost. And there's still pretty high premium for LTE chipsets, and there's a lot more patents and licensing involved, which goes into that. So in this case, to talk a little more about the cellular module. These are available. You basically plug one of these down. It comes mostly pre-certified. You provide your own antennas typically, and you can get them for different carriers. You can buy them that work anywhere in the world. Of course, you pay money for any of those extra features. If you want, every band ever, well, that's dollars. So one of the biggest challenges with cellular is understanding your global market. Even a company like Apple has to have multiple SKUs of iPhones in order to support all the different carriers around the world. So that's one of the biggest challenges with cellular. First you have a very high upfront cost. Then you typically have a cost to support multiple products, and that can be a real challenge. And something I should point out here while I'm on this, in terms of the Z-Wave, one of the biggest issues with the Z-Wave is while a module might cost you less than Wi-Fi, you also have to take into account that they may not already have a router. So the customers have to buy a hub as well. And that, if you look at it in a package sense, you can often amortize out the cost of the hub through your savings. But for single devices or a couple devices, that can be a very significant part of the cost. If you're buying a $20 light switch and you have to buy a $25 hub for it to work, that's a really bad customer experience.
For the certification, are you
including encryption? So no, I'm not including encryption in any of my certification. Obviously, that falls more. I'm referring to wireless certification. Bluetooth, Z-Wave, and Wi-Fi. You simply have to have FCC approval. Cellular, in addition to the FCC or whatever the local governing body is, you also have to have carrier approval, which proves to be a much bigger challenge. Encryption ends up being, there's obviously export license controls and things like that where your encryption standards can go, but no, I'm not really including that in this. Any other questions?
I don't in terms of FCC certification process, they require to turn on the inscription.
What's that?
Let's say in the FCC certification process, let's say you go to a local lab, UL, or any lab for the certification. I don't think they care much about your software there. They more care about all the way power, right?
Yeah, so the FCC basically is designed to test worst case real world. So, if you have something in your system that limits your maximum transmit interval, and it can actually be in software, and if it's hard to enforce in software. So, if you have a Wi-Fi device that you want a higher output power to a limit, you can reduce your transmit interval and say, well, I will transmit no more than 50% of the time, and that will directly affect your bandwidth and your throughput, but not your, but it also decreases your average radiated power.
So I have one question, I'm little curious. You put 4 fruits, but your cost is 15 times, and if you go back, no fruit is 15 times cost difference.
Yeah.
Right?
What fruit should I put that costs 15 times as much? Avocado. Cellular is the avocado of the world. We all know. It's just too expensive.
One cherry to one avocado.
Yeah.
Yeah, you could, but how about that?
So back to Wi-Fi certification, it's enforcement of a good neighbor policy.
Yes.
What it is.
Yeah. So it's actually one of the theory behind the FCC is really noble. There are some challenges with how they've chosen to enforce that and what some of the specs are, and there's a lot of gray area, and that's also one of the big challenges is, when you're buying, FCC certified modules out of China, it's self-certified. They've produced a lab test result, but at the end of the day, you're responsible for your product. If it goes out there and there's a software bug in it that causes transmitters to go and just blast out, and they get any FCC complaints, you're the one that has to go back and fix all those products. Yeah.
Usually you have a Wi-Fi Alliance logo which requires you to pass to have WPA too. Yeah,
so the Wi-Fi Alliance, there's to actually be a member, and Bluetooth, Z-Wave, and Wi-Fi are similar in this standard. They're Bluetooth and Wi-Fi are similar. It's an open spec. Anyone can implement Wi-Fi without additional license fee. If you want to use the Wi-Fi logo, this trademark logo in your marketing materials, you have to become a member of the Wi-Fi Alliance, or at some level, you have to pay them money. Is what it comes down to, and you have to pass an additional set of compliance and interoperability standards. The same thing is true for Bluetooth. Z-Wave, I'm not as familiar with that. I'm pretty sure you have to join the Z-Wave Alliance in order to use the Z-Wave anywhere in your marketing material. I'm not sure whether that is licensed to you as part of buying the Z-Wave module.
So on some consumer products, I only see it states 802.11 BEG and compliance, and without the logo, I think that they are not required. They don't have to pay for the WPA.
Yeah, so you can, and there are a lot of companies that have put logos that look like the Wi-Fi Alliance on their stuff, and some of them have been sued. I would actually say it's more common to not be a member than it is to be a member. Apple isn't a member. I don't believe Google is a member. There are a lot of large companies who have chosen they will come up with their own Wi-Fi branding strategy, and they have to do interoperability testing because they want their stuff to work, not because they want to use a logo.
You say Wi-Fi without logo.
Well, they come up with their own logo, so you can do anything you want.
The term Wi-Fi is a trademark.
So you can use Wi-Fi in text, and you can come up with they lost that. They wanted it, but yeah, if you look at the back of an Apple box, it definitely says it has Wi-Fi. So my understanding is you're also allowed to use the 802.11 specs without license.
So the Wi-Fi logo, that's more of a marketing and branding alliance that was formed to, educate the mass consumer base, right, about interoperability. And it's probably kind of outlive its useful purpose.
Yeah, so they're, you know, and it depends on the company, and it's all about choosing what is right for your company as to whether you want to join the Wi-Fi alliance. If you don't have a marketing department and you want to for making a Wi-Fi product, it might make sense. So, yeah.
If you read the box on Apple, it's got all the list of the 802 standards.
Yeah.
You know, A, B, G, A, C, whatever it is.
Yeah. So
That's all IEEE.
Yeah. My understanding is basically you can put anything in text you want. Only the logos are trademarked. There are no copyrights on the individual words or technologies. Yeah.
How about Wi-Fi Direct? Wi-Fi Direct is owned by Wi-Fi Alliance.
So my understanding is Wi-Fi Direct is the same basic setup where it's an open spec that anyone can implement, and only if you want to use the Wi-Fi Direct logos, then you have to join the Wi-Fi Alliance. So cost, yeah. So this is probably my favorite slide in the deck, because, I mean, honestly, like, I've spent a long time looking at wireless protocols, understanding wireless protocols, understanding security, fundamental security models, things like that. And if I could have you take away one thing from this meeting, like, as an engineer, the thing that I wish all engineers understood is that security is hard. It is really, genuinely, truly hard. Even in this day and age, 2014, security is hard. Because every time we engineer something new, there's some new security issue that it introduces. Every smart feature, every auto update, every piece of hardware you put in there introduces potential security flaws into your product. And when we start talking about connected products, that starts being a huge problem. A great example of this is Bluetooth Smart. They put in actually pretty good encryption. It's nice and standard AES 128. It's strong enough for 99.9% of things. Maybe not my bank, but you know, my Google search is sure fine. And then they put in a really bad pairing. There are 10,000 possible keys for Bluetooth. Would anyone like to put it out here? Damn. It takes about 1.2 seconds to cycle through all 10,000 of them. That's not cryptographically strong. And what's even worse is 90% of devices all use the same key to the extent that they branded it. There's the Bluetooth just works, which means that the pin code is all zeros. So there have been real demonstrated working attacks on Bluetooth. Yeah?
Right now they use NFC to do the pairing.
So you can do NFC to do pairing. There are secure methods. The fundamental data transfer is not insecure. It's that most of the devices, the way they do pairing is insecure. It is possible to do secure Bluetooth if you use out of band. Basically, that means you can't use any of the built-in pairing mechanisms.
So the thing where you're matching numbers on both ends is pretty good.
Yeah. So the way the attack actually works, So Mike Ryan demonstrated this attack at Black Hat in August of 2013. He used a laptop, Wireshark, mostly built-in open source tools, and a $100 open source Bluetooth adapter called the Ubertooth, and was able to implement this hack in a couple months of security research. The concern about this is that it can be formed anytime. It's completely passive. You have no idea that somebody has your data. And Bluetooth doesn't ever change the key, which means if I come into this room and I crack your Bluetooth today, and I see you next week, I will have the same key and I will have your same data. If you are wearing a Fitbit or any kind of other personal, tracking device, this should concern you, right? This means they have not only, maybe your health data, maybe you don't care about how many steps you've taken, but I now have a unique device that identifies you. And I can crack in and I can capture that device. And one of the things, that starts happening is, I don't think any U.S. retailers are crazy enough to do this. But what starts happening when other retailers and people who are not reputable start tracking you and selling that information? It starts being a serious security concern.
That brings a question. Today we have a 5 wearable computer devices. In the 10 years they are saying 50 devices. That means security will be 1,000 times difficult.
So security doesn't have to scale with the number of devices, right? The point of this is really that you can design, you can use great, trusted, you're like, hey, I'm going to secure this, and I'm going to use industry standard encryption, right? AES-128 is used everywhere. But if you then make a marketing decision that says, well, I want it to be really easy to set up, that always introduces complications. And that's what ended up happening with Bluetooth. The companies who are really serious about Bluetooth and are using it in security applications, front door locks, things like that, have to put their own layer of encryption on top of this. That provides that's a tremendous effort. Now you have to hire security experts to develop your product, even though the protocol you're using already provides a layer of encryption. It also increases your power consumption, right? The chips already do the AES-128 in hardware. But if you're laying your own on top of that, you're probably doing it in CPUs. Longer wait times, more compute cycles, more battery life, less battery.
It goes back to that trade-off between ease of use for the consumer, because initially when we did Bluetooth, the pairing was you generate a 8-character random string and then have a thing to mess it up. You have 12 seconds or 18 seconds to get it. Right. And then they just throw that thing against the wall.
Yeah.
You don't want a lot of stuff broken being returned to the best time.
Yeah, so
okay, I'll make it easier.
Providing passphrases or PIN codes, and the reason that they're all zeros is like, where are you going to take in a passcode on a Fitbit? I mean, right? Like, there isn't even a button. Like tap it. It's inconceivable to come up with something like that. So it is possible to do out of band pairing. Right, you could have, if it's got a USB connector, you could sync with your computer and exchange keys through the computer and things like that. But it's kind of a shame because it really is, they got it 95% right, but because of one mistake, they've sort of lost their security.
Also, the thought was that proximity is going to help. So you have to be open, both devices have to be in discovery mode, they have to be near each other. And there's this short window to do the pairing. And then once it's paired, it's locked, right?
Yeah. So the challenge in Bluetooth was there was a known vulnerability in the pairing mechanism. If you observe the pairing, you can capture the keys. This is a general problem with security. How do you exchange something over the air between 2 unknown devices? The issue, and so in theory, you could pair it inside of a Faraday cage or whatever else, make sure everybody has their keys. The challenge was in Bluetooth Smart, they introduced a repairing mechanism, where at any point in time, the device can request repairing. So all the crack does is it spoofs the device and says, please repair. The master says, sure, and does a repairing, and at that point in time, you observe the repairing and you capture the keys.
Yeah. Okay. Maybe an answer to what I'm about to ask, but this sort of feeds off the last comment. Would it be obvious that your device is now paired to the wrong device?
So the crack that Mike Ryan demonstrated, basically it disrupts the communication temporarily. It doesn't change the pairing.
It's a pair partially observed.
Right. So basically what happens is you break the pairing, you tell them the pairing is broken, they repair, and you actually don't inject into that, you observe it. And what happens is you now have a key, and now you can decrypt all the traffic sent each way. So you're not actually polling the device, you're still reliant on it. It's kind of insane because it means your phone becomes part of the attack vector, right? The thing that's actually querying the information is the one that is allowing somebody to passively pull the information out.
So the owner doesn't see that happen. Does it happen in the background?
most of the devices are silent about it. There are some devices apparently that basically require a button press to do a repairing as well. But that actually means they're not spec compliant. So.
Isn't that what somebody did last week? Outside a building full of, I think, Bluetooth lights, they added one light, they put a network.
So that was actually, yeah, so that was actually 6 low pan, which is different from Bluetooth. It's another great example. Security is hard. What actually happened there, traffic was all completely encrypted. And there was no security mechanism in that. What wasn't encrypted was their flash. So somebody took apart a bulb, read out the key that was being used for every single light bulb in the field. Every single light bulb they ever sold all had the same key. I won't be buying front door locks from these people. And once they had that key, they were able to decrypt all the traffic, join networks, look for the pairing, and then inject malicious code into the system. What was the name of it? That was the LifeX. Yeah.
So I know you're getting a little ahead of you, but 2 questions, maybe indirectly related to security. The first one is, do all of these systems include an IP stack? And the second is, do all of these systems require recognition of priorities for, say, for example, Wi-Fi is supposed to be 6 levels of prioritization.
So to answer your question, Bluetooth Smart and Z-Wave do not run IP stacks. Typically in Z-Wave, you have in the hub, it is actually doing, there'll be generally a small Linux computer. They're also So Bluetooth, there's been the accessory makers all would like to add IP support to Bluetooth. Basically, this would allow your phone to look more like a hotspot and less reliant on an app, right? So currently, your Bluetooth device does not talk to the internet. It is reliant on a app to make those connections for it. So when you want to upload your Fitbit data to their cloud, it actually goes to your phone, it gets sent in, it's sitting inside your phone. It has no idea that where it's going on the internet. I think the app takes care of all of that. The accessory manufacturers don't like that because it means, you know, they're stuck by the rules of the OS in terms of what data they can pass on, they can pass it. But of course, the phone manufacturers think this is a great idea because it means they can control how much data is being sent and when it's sent.
But it's also, I mean, it's a little laughable given your last slide, but it is more secure.
It is more secure. Doing cryptography in typically your Bluetooth device has a Cortex M0.
As opposed to making this attackable from the entire internet.
Right. You know, where you have a lot more resources to do those things on the phone. So the idea of running a TCP/IP stack on a Cortex M0 with 4 to 32K of RAM alongside your Bluetooth stacks seems not quite feasible yet.
So it's just a smoking gun.
Yes.
Cisco is always looking to the future. That future doesn't always come. And the biggest challenge I see with putting IP on Bluetooth is it's actually really bad for your phone. Has anybody here ever put their phone into hotspot mode where your laptop can tether and your phone gets really hot and the battery's dead in about an hour? I don't really need my Fitbit doing that as well. The reason that it gets hot isn't because transmitting Wi-Fi is that much higher power. It's that it has to keep the radio on all the time. It has to be firing up for every single transaction. Every time your laptop hiccups, it's like, well, better fire up LTE. I don't need my fitness tracker telling my LTE to turn on. I'd rather have it be buffered in the app and sent the next time the phone makes a connection.
And if it's LTE, it goes on your bill.
Yeah.
So you're hearing anything good or bad about CE-IP?
I haven't heard anything about it now. Yeah.
Here with your 4.1, they can coexist with the classical Bluetooth. Classical Bluetooth have a long profile which use TCP/IP.
Yeah. So there are some of the emerging technologies. 4.1 has been standardized. We recently ratified that. And so it is a technology that will be available. It's unclear whether it is, and it's certainly technically feasible. Right? Nothing about IP over Bluetooth is hard, but to do it at these costs, to do it in a meaningful way, in a way that customers want, getting support from the phone manufacturers is all a big challenge. So I'm going to try and keep moving through security. I have no idea how time it is. We're almost halfway. Almost done talking, so I'll try and be a little quicker. So Z-Wave, the LifeX is not Z-Wave, but several systems had similar issues where they had a fundamental security flaw in them. There was nothing inherently insecure about the protocol, but one manufacturer implemented something in a bad way, and all of the devices were vulnerable. Now, in the case of the LifeX, they had built-in system upgrades. So they were able to swap out the encryption key, they were able to upload their new version, and to lock down the flash to prevent readback. So Z-Wave, the security holes that have come up in that, and mostly then, it's not the protocol, it's how it was implemented. And so it really highlights the need to have the ability to update your system to fix security holes in the field. I guarantee you, if you ship a product, you will have a security hole. It is just infeasible. I mean, even the most tested security, anybody ever heard of Heartbleed? Right? Like, what happens when that's an embedded device? Right? What are you going to do? You're going to go to the customer's house, so you can upgrade it? No. You got to be able to update it in the field remotely. That's one of the great things about connected products. It's the double-edged sword. It's that you can do this, but you are also required to do it because of the complexity of the system. Wi-Fi, WPA and WEP have both been cracked. There's still a lot of customers that use them in their homes. If you're building a secure product and you want to support these, you can't rely on the Wi-Fi network security. Additionally, home network is not that secure. Even in an office, right? We have our password written on a board, and people can get in and yeah. So Wi-Fi has a layer of encryption, but really you need to be building your own encryption on top of that. Cellular, sure, it goes secure to the NSA servers, but then it has to come out from there. Cellular servers. Data centers.
You're probably right.
Yeah. So at this point, this is 2014. We need to be encrypting data that's on the internet. If you're on the internet, that data has to be encrypted. That's the modern story. It is no longer acceptable to do things that are security through obscurity or anything else. Real, actual, cryptographically secure end-to-end applications are going to be required if you want to be a player in the internet base. Power consumption, this one is relatively straightforward. I don't think people will be terribly surprised by this. Bluetooth low energy is low power. The Z-Wave stuff tends to be a little bit higher power. A lot of that depends on whether or not you have mesh networking turned on. Mesh networking always increases your power. That's just how it works. Wi-Fi is interesting, and really one of the things to think about all of these is the second most important thing I teach you today. Remember, security is hard, and one other thing is that for most of these devices, it takes more power to listen than to transmit. Think about that. You spend more of your energy waiting to hear something than you do actually saying.
You have to spend more time doing
It's because you spend more time doing it. Synchronizing clocks and things like that is extremely challenging. So the idea that you're going to wake up and the packet's going to arrive at just the right time is not very likely. The reason Bluetooth is so low power is the device, your device, never has to listen except right after it transmits. Basically, it goes, I'm here, and it listens for like 4 milliseconds or something in the order of milliseconds, and then goes straight to sleep. And so when it's doing nothing, it just wakes up, sends a broadcast out. If anything comes back, then it stays online and transfers data, but it means it can be extremely low power. And that interval is adjustable. Apple has set some rules for iBeacon, but almost all of these are based around duty cycle. And it's all about how do you decrease your duty cycle, and it's almost always decreasing your duty cycle with listen. Cellular has, because they own the networks, they get to design them, is exceedingly well designed for listening. It has to be listening all the time because you have to be able to receive a phone call. But they have special dedicated channels built in that are out of band, are lower power, they're dedicated for just being notified of the event happening, which means you power down your DSPs, and it uses a different encoding. Wi-Fi, most routers have power saving abilities built in. Of course, I want my phone to have really good battery life. I want my laptop to have really good battery life. They shouldn't have to be listening to the router all the time. It's typically, so DTIM basically it's a buffer and notify system where you can sleep for 100 to 300 and sometimes more milliseconds without checking in with the server. Z-Wave, as soon as you start getting into mesh networking, it gets very challenging. That's one of the reasons most of the devices don't do mesh. And many of the devices, if it's running off the point cell, it is not doing mesh network. It's waking up, it's sending a packet, and it's going the heck to sleep. It's not even waiting for an act. Yeah.
If your device is talking to Wi-Fi in the cell phone, then you have to worry about the cell phone going to sleep in the Wi-Fi sense. Because Wi-Fi directly, access point can go to sleep.
Sorry.
Not infrastructure there. Access point don't go.
So the access point doesn't go to sleep. The phone, when you are inactive, you'll basically reduce if you're waiting for incoming data. So anytime you have Wi-Fi, anything you have active data, you just transmit it. Next time there's a channel open, you don't wait for a particular event. But if you're sitting there waiting and you don't have any data to receive, and again, it's done with an exponential backoff where if you haven't received anything in 50 milliseconds, you go to sleep 50 milliseconds. If you haven't received anything in 100 milliseconds, you go to sleep for 100 milliseconds. And it doubles up to your maximum, which is typically 300 milliseconds.
Yeah, because the Wi-Fi directly has provision for the access point to go to sleep in two more, right? One is opportunistic.
Yeah. So with Wi-Fi Direct, because the idea there is that you don't have an infrastructure piece, you're talking phone to phone. Basically, it's doing the exact same thing, but both the access point and the router, both the access point and the device are able to sleep until that interval. Any questions on power consumption? Yeah.
So one of the things is you have to kind of trade off on latency. You get super aggressive on power savings on Bluetooth mouse.
Yeah.
User moves if nothing happens.
Yeah. So latency plays into all of this.
On a switch, like you go to the dimmer, and nothing's happening.
Yeah, and so one of the things you have to sort of think about when you're designing your product is, are you latency sensitive, right? If you're collecting temperature data and you're sending it to the internet, you are not latency sensitive. That temperature is not going to care if it gets there 300 milliseconds later. If you are a light bulb and you are waiting for a turn on signal, you are definitely latency sensitive. And so finding those applications, understanding your needs and how that affects your power story, this is, in my experience at Electric Amp, power consumption, understanding it, and your power story for battery-powered devices is the #1 challenge for our customers. Most people want to just sort of stay online all the time and just be always accessible and whatever. right? And then they say, oh, and by the way, I'm going to run off of 2 AA batteries, I'm going to get 2 years of battery life. And then they don't, and they're surprised. So the biggest thing we do is educating people on how power actually works. And most of these, like our low power devices, are mostly based around only waking up when you need to do something. Wi-Fi is very quick to join, cellular is very quick to join. So powering down, disconnecting when you aren't doing something is an extremely effective strategy for certain classes of devices. Again, temperature sensor. Power down your radio between readings, right? You don't need to take temperature readings more than once a minute. And if you do, buffer them and only send them once a minute. Very rarely do you have something that's that time critical when you're collecting data like that. But again, if you're a light bulb waiting for that signal, that's not an option for you. You can't power down and check in. Oh, well, I'll check in a minute if somebody has turned on the lights, right? Like, it's going to be a bad time. Your product's not going to do so well. So.
Changing TV stations.
Yeah. Sometimes I feel like my TiVo takes a minute. So complexity of implementation. So this is my as promised, the one place that I will switch between electric and Wi-Fi. I like to think our platform is exceedingly easy. Very proud of it. And we spent a long time debating on the Z-Wave and the Bluetooth. You know, they're both a little more straightforward. One of the main advantages and one of the main reasons for that is you typically have a hub that's doing the real heavy lifting for you. If you're trying to develop a complete solution end to end, those bars both move to the right? With Bluetooth, you're talking about building an accessory. You're talking about having a cloud infrastructure. You're talking about having an iOS app and an Android app. That starts being a lot of engineers that are doing very different things. Collecting those people is a significant challenge. When you move to Wi-Fi, on top of all of those things, you're talking about having reliable TCP/IP stacks, right? You're not just plunking down Linux most of the time. You're actually doing it on a microcontroller. How do you do cryptography on a microcontroller? It's hard. How do you do, how do you deal with all of the routers out there that don't comply to the standards? We found things that do things that are explicitly forbidden from the spec. Zero-length passwords, right? You have to be able to test these things, try all of that, and all of that's on top of your complexity of an already very complex product. Cellular, you basically get all the Wi-Fi stuff, plus you've got some nice AT modem commands in there that obscure things. You're dealing with how cellular radios actually work is extremely requires a lot of learning. So that starts to really push it out. And I'm going to get to it, but certification for cellular is a task. Are there any questions on complexity of implementation? Yeah.
So, do I need to do anything to my software to develop?
So you don't have to do anything. So put on my marketing hat for a second. Basically, we provide tools to get it online very quickly. We're involved in, if anyone here is interested in playing with them, we're already active in the developer community. You can get our stuff on SparkFront, Adafruit, DigiKey, Seed Studio, and you can buy it and download our app. And you can fire it up and be writing code and write everything in the web browser, and it downloads and runs automatically. You get a small cloud presence with every single device has a cloud presence as well. So we do a lot of prototyping and stuff like that. I have a system in my house that I built, designed the hardware, wrote the embedded code, wrote the cloud code, and wrote an app to control the fans in my house. They're all for 304 megahertz, reverse engineering the protocol, and everything on that. That was a personal issue for me. Was I really like falling asleep with a fan on. I really hate waking up at 3 a.m. freezing my butt off. So I just have it internet connected, and I have a schedule I can set on my phone of when it turns on, when it turns off, and it's all really very easy. And that was a project that, including hardware, took me less than 2 weeks. So data throughput, again, I'm going to emphasize this is probably the least interesting thing you'll see today. Most IoT applications are transferring incredibly small amounts of data. The only time it starts mattering is if you want to do video and probably audio. So Bluetooth 4, right? This is not the audio version. This is the low power version. It does not do audio. Z-Wave definitely doesn't do audio. So Z-Wave is maximum throughput of 40 kilobits a second. Bluetooth gets you up to 1 megabit. Cellular, well, they change that every 3 months. I don't know what they're running in Korea now, but it's over 100 megabits. Wi-Fi, we're getting to gigabit. Again, once you get beyond, I mean, really, honestly, if every one of these ran at 40 kilobits, they'd still be fine. You wouldn't notice. It'd be A-okay. Most IoT applications use very little data. Yeah. So our performance is so we can go up to 73 megabits a second. Typically, that ends up being capped by your TCP/IP buffer sizes. So if you're willing to allocate more of your application space and you have a very low ping time, you get your TCP acts fast enough that you can do meaningful amounts of data in several megabits. Internet connectivity is the other really important thing to think about. Bluetooth and Z-Wave are not connected to the internet. They are not running TCP/IP stacks. They could not go to weather.com and check the weather. They have to rely on some other piece of infrastructure to do that for them. In the case of Bluetooth, it's almost always your phone. I have yet to see another central device besides a phone. What's that?
Bluetooth keyboard.
Keyboards are peripheral. Sorry, I should say phones and laptops. Laptops can act as centrals, but that's about it. Almost everything else is acting as a peripheral. Z-Wave, again, you're also always buying a hub in your house, which is really just a Linux box that's packing up those data packets and sending it to server. Wi-Fi. Wi-Fi is not the same thing as internet. It's something that I've tried to explain to my mother. Says the Wi-Fi is not working. It's like, well, can you connect to Wi-Fi? Yeah, I can connect to Wi-Fi. Google doesn't. It's like, okay, so your internet's not working. This is a mistake we've seen a lot of people make. My favorite was when we were looking for products to stick an into. We found a hot tub that was Wi-Fi enabled. We're like, great, all the VCs can buy this hot tub, they can put it at their house in Tahoe, and they'll turn it on when they're driving up there, VCs drain. It turns out that, and so we're like, well, maybe it's local. No, it's worse than that. The hot tub had an access point inside of it. And the way you set the temperature on the hot tub was you actually had to go into settings, change your Wi-Fi network to the hot tub's Wi-Fi. And then you could load a web page. And it's basically like configuring your route, right? Which is like just a god-awful experience. Something I tried to do exactly once. And it was so clear that this company had said, well, we need Wi-Fi. And what they meant was it needs to be internet connected. And some contractor said, yep, it's got Wi-Fi. Check. And so it's a really important thing to remember that not every Wi-Fi device is internet connected. And if you're building IoT, that's an important distinction to make. And so that's one of the things we distinguish about with the electronics. It provides a pipe through the firewall, through to the internet, and actually gives you a URL for your device.
It's a replacement for last hop ether.
Yeah. So, important distinction.
So do you have all the piping to tell it through, like firewalls and everything?
Yeah, so to talk a little bit about the electric solution for this, so we basically have a server that accepts incoming connections. You can think of it like an old school modem bay that gets you online every phone's home. It opens a secure outbound connection that is all encrypted, which means basically you don't have to think about how the data gets from there to our server. And then from the server, you actually write a piece of application code that runs on our server, and that's responsible for piping the data wherever on the internet you want, or fetching data. So our strategy is, rather than say parse XML from weather.com on a microcontroller, which sounds unfun, let's do it on a server in the cloud and only send the meaningful information down to that device. Cellular, they're the most connected products, right? You basically, you spit data into it, it comes out at a WAP, and it's on the internet. There's no extra hops. And that's what everyone buys their data package for. My LTE only connected me to other LTE subscribers on AT&T. I wouldn't be very happy. I want to go to Google.com. Yeah.
So if I want more data from Bluetooth than even Wi-Fi, but wirelessly, not K1 line, etc. What is the next one?
So it starts to get a little bit outside of the scope of IoT. I mean,
Or for home use, is there anything to buy, or is there nothing available?
So
wireless.
Wi-Fi is improving, right? So it'll just be, you go to 802.11ac, you start getting really fantastically complex people who are getting PhDs in signal propagation sort of stuff. And, I think that's where we'll continue to see improvement. One of the things with even Ethernet and things like that in the home, there's, once you get to a certain speed, once you can stream 3 Netflix HD movies, right? Do you really need more bandwidth, right?
Do you need more bandwidth in your home than your access link provides?
Right, and that's the big thing now. Is unless you're getting to Google Fiber, 802.11g will do you just fine. Interoperability. This is really important to think about when you're designing a product. Wi-Fi is probably the most global wireless technology available. I have every confidence that I can take my laptop and go literally anywhere in the world and be able to get on a Wi-Fi network, and that would be provided in every hotel I go to, internet cafes, things like that. It's just everywhere. That becomes important for IoT devices that want to have some mobility. There are a lot of free networks out there that you can promiscuously join. Bluetooth is also extremely interoperable. The biggest challenge there is, does my phone have BLE? I don't know. Right? Oh, I have an iPhone 4. I bought this thing. It doesn't work with that. That's going to go away as those devices roll out of the market, and the market thinks BLE is supported on almost every phone. That'll be really common. Cellular, you obviously have lots of different carriers and different bands. That makes for challenges. If I have a T-Mobile phone, can I take it to Europe and have it still work? Well, yes, but. And then Z-Wave, biggest issue with Z-Wave is the closed system. Only Z-Wave products talk to other Z-Wave products. And even then, one from different manufacturers have traditionally had trouble. That's the promise of Z-Wave is that they will all be supported and it will be magical and unicorns, and every unicorn will be able to fuck every other unicorn. And it's something that hasn't really been delivered on the market. Are there any questions on this?
T-Mobile is the one that does work.
Well, T-Mobile and AT&T work in Europe, but T-Mobile doesn't have LTE in Europe. Certification. The good news is you can buy pretty much pre-certified modules. This means you sort of plug it down to your board, you set your test report, you just have to do sort of standard level FCC testing. Those are available for Wi-Fi, Bluetooth, Z-Wave. You're obviously paying a premium for that. Somebody else has gone and spent $20,000, so you don't have to. That costs you some money. Cellular, I promise you we can get to this. Cellular this is again a logarithmic scale. Let's just say that. It is orders of magnitude more complex than developing a Wi-Fi, Bluetooth, or Z-Wave product. And that's because you have multiple bands that are operating. Most cellular, you're talking about 5 bands at a minimum. Right? Your modern iPhone is at 7, and our device is moving to 8 bands. That's a lot of test time. That's a lot of antenna tuning. And every one of those changes resets everything. As soon as you have those interoperating systems, it's extremely challenging. Now, let's say that you go and you buy somebody else's antenna, and you buy a pre-certified module, and then you say, AT&T, I'd like to put this on your network. And they say, well, here's the thing, you're going to have to go through our approvals for that. And AT&T sends you to PTCRB, which is an acronym that no longer holds any meaning other than the fact that they're the gatekeepers to AT&T's network. AT&T has been, because they want people on their network, has been improving the process of PTCRB. They released a white paper last year. They have successfully dropped the cost to $40,000 in 6 months. If you know what you're doing. So, if you don't know what you're doing, plan for a year and 100 credits. Yep.
But for CDMA carriers, you don't have, you just have to certify with that carrier, you don't have to.
So CDMA carriers, if you're willing to restrict yourself to a single carrier like Verizon, you can go through Verizon's approvals, and they're not always as hard. A lot of it depends on whether Verizon wants you on their network. My understanding, I haven't worked with Verizon directly, but is that they have the ability to help you through the process, and they have the ability to hinder you. And so it's still a big question mark and it can be quite scary. And that only gives you approval in the US on Verizon. There are a lot of other shortcuts you can take. There are other MVNOs that will certify you. All of these are, and nobody is willing to tell you straight up, yes, you can do that, no, you can't do that. And so you can get a product into development, you can bring it to market, and AT&T says, well, wait, that's connecting to our network. You don't have the right certifications. Stop your product, give us $40,000, and have fun in the lab. So it's a major risk, and you need to be very clear about what you are taking on when you're designing a cellular device. It is not the same thing as doing Bluetooth or Wi-Fi.
The certification of LTE release 10 requires backward compatibility for CDMA, UMTS also.
I'm not familiar with that, so
those are I think release 10.
Yeah,
after
so
release 10, you cannot call yourself 4G.
Yeah, though again, most of the IoT devices we're seeing are not moving to LTE. They're mostly on 3G. The LTE modules are just still too expensive. You take that $30 and you double it to put in LTE, and very few devices outside of laptops and phones actually require that kind of throughput. All right, we're almost done, I promise. Customer recognition. I talked a little bit about this earlier. Z-Wave. I mean, how many people in here had heard of Z-Wave before I started talking about it? Okay, a couple. How many people own a Bluetooth device or have one with them? How many people have set up multiple Wi-Fi networks? And cellular is, without a doubt, the most pervasive global technology on the face of the earth. There are more users online in China using cell phones than there are using laptops. It is just, everywhere. They know what carrier they're on. A lot of them know the difference between 3G and 4G. Consumers are extremely well educated when it comes to cellular. And if you put AT&T's logo on the outside of your box, that's an instant sign of recognition that that product will work for them. This becomes really important when you have, people like us, engineers, generally have enough background knowledge to understand these things. I always use my mother as my example, which is maybe a little mean of me, but, I sort of think it's like my mom knows that she has Wi-Fi, and I think she actually knows the password to her Wi-Fi. She thinks she has Bluetooth, she probably does. She's got Bluetooth in her car, but that doesn't mean that she has Bluetooth low energy, right? She might have an iPhone 4 that pairs with her card, so it says, oh, well, this has Bluetooth, I'll use that. And then it doesn't work. So, And then Z-Wave is relatively uncommon outside of people who are very familiar with home automation. So I'm going to sort of go through a little summary with each of these. These are things that I think are important about them. The sort of differentiators here. Bluetooth Smart, low power, it's king right now, and it's getting better. It's staggering what the chip manufacturers are doing with Bluetooth. It's really awesome. Low cost, again, it's just plummeting. We've seen cost halve in the last year, and you're getting something that's lower power, better battery life, more everything, does more stuff, and it costs you half as much, and it's half the size, right? It's spectacular. Security is a big question mark there. Can you actually do it for security? Do your customers care about it being secure? What kind of data are you transmitting? And then the thing to think about, for some applications, it's very phone-centric, and that kind of translates to person-centric. That most of the time, it's about something that is moving with that person, and it's really an extension of the phone. And it kind of calls the question, is that actually an IoT product, right? If it's just an accessory to your phone, we generally don't think of the phone, it's a way of augmenting your phone. That's not really IoT, right? That's, well, I have a phone, and it also collects information about me. You want to think about that and think about whether that's what you're looking for. Z-Wave, low power. Again, it's not as low power as Bluetooth, but you're talking about small battery powered devices that are some like remotes and things like that for point of sale. They're very dumb devices, not really connected. The cost is pretty good. It's relatively low if you're buying a large suite of products. If you're amortizing that hub, if you want to put something in every single light bulb, it's not a bad way to go. If you're trying to convince a customer to buy one of something, it's going to be a really hard sell. In-system upgrades, because of the low data rate, this is something where that starts to be painful. Being able to upgrade the OS and all the applications running on an individual device is really challenging. It's not typically built into those modules. They haven't thought about that aspect of it. It's something you have to roll on top of that. And because of the low bandwidth and the mesh network where you can have multi-hop, every time you hop, you have the bandwidth. So you get 4 hops out, and you're talking about 5 kilobytes a second. It starts being a fairly long time to move OS upgrades and an application go back and forth.
Since the new Z-Wave, the old one is even slower.
Yeah, that 40 kilobits is the maximum speed. The old one, I think, was like 1.2 kilobits.
9600 baud.
9600 baud, yeah, so sorry, it wasn't quite 1.2. And it's actually, it's not a self-healing mesh. It's very oriented towards, I'm going to install all of these things, and then that's it. They're never going to change forever and ever. If they do, I have to call my home installer back to set everything up again. That works well for home automation and some of the security applications. That's mostly where you see these being adopted. If you're buying, you see it find door locks and things like that. I'm going to go back to security. It's a question mark there. If you're looking to be in that ecosystem, great choice. Well, it's a reasonable choice. Wi-Fi is, you get to sort of moderate power levels. It's possible to do long-term battery powered applications, but requires significant thought. Requires, temperature water, sure. Low power light switch that runs off the batteries. So you have to understand that. Moderate cost, you're starting to get into more complex, starting with that pretty serious processor. Most of them are running Cortex, running bigger processors. That again goes back to your power consumption. The great thing about Wi-Fi, again, like Bluetooth, costs are just coming down precipitously. I wouldn't be surprised if a fully hosted Wi-Fi cost actually CE in the next year. It's just, there's just so much volume and so many players. Everybody's rolling out their own Bluetooth and their own Wi-Fi, and they're gobbling up all the companies that have the IP. Some of the drawbacks are networking is hard. If you're doing TCP/IP on a microcontroller, you're doing security on a microcontroller. These are challenging things. And a lot of hardware, traditional hardware companies who have the expertise to manufacture these devices don't have the expertise in software. Even somebody that's making routers right now, they mostly rely on Linux or another software application. They don't really understand how to do those network layers for them, and then patching them and things like that to make them work with the wide variety of networks that are out there is really challenging. Another drawback is Wi-Fi is very building centric. It's not likely to be in a field in the middle of nowhere. If you're trying to do an agricultural soil moisture sensor, Wi-Fi starts being a challenge. You need to have a real custom setup for that. But in homes for consumer electronics, it's a great fit. And cellular, security is a great advantage here, right? SIMs are just the whole thing, right? You're having to pay somebody for this. They make sure it's secure. They want to get paid. It's extremely low. It is far away. It's mobile wireless standard. There is, with a worldwide module, you can go to even very remote places and have decent coverage. Power becomes a problem. We're used to charging our phones every day. If I had an IoT device that I had to charge every day, that would be an issue for me. And you kind of get into the awkward phase where it's like, well, I'll put a bigger battery in, not space constraint, I'll put a week-long battery in. And then it's like, well, now it just drains so slowly that I forget to charge it, right? Now it's sitting there dead when I need it. And that really limits its mobility, right? So you start looking at like some solar applications, totally equitable. Again, if you're going back to agriculture, cellular plus some solar is a pretty good fit. High cost, not only the higher cost of the module, but then the higher cost of the actual connection. You got to pay a carrier, you got to buy that data, and knowing how much data you're going to be using is a big challenge. And the big killer for cellular is certifications. You really want to know what you're doing and really have to commit to a project if you're going to go down the cellular route. Yeah.
Well, things like Kindle have a cellular network connection, but it's low cost because it doesn't do audio, obviously. So what are they doing different? I mean, is that a different price chipset than your $30 chip? Is that with audio solutions and there's a WhisperNet solution that's cheaper? Or how does it do that?
So I think the hardware is the same. There's not really much around that. In order to be a good player on the network, you have to support a lot of these things. Really what they've done is they've used their buying power to negotiate extremely good deals on the data and to buy it in large chunks and then basically eat that cost. So there are a number of end-to-end carriers out there. You're not, realistically, nobody wants an IoT cellular device that in addition to the $30 upfront costs you $30 a month, right? We're not talking about cell phone plans here. Most of the carriers have either dedicated end-to-end divisions or they sort of subcontract it through some other way. There are lots of people who buy and speculate on data, right, where they go around and they buy up data and then it sort of, they push it around and you can basically buy a SIM card that says, well, I'm not going to guarantee what network you'll be on, but your data will get through and they can actually then make it around. Yeah.
One of the wilder concepts for engineering things is this idea of a swarm of bots that are all flying around and communicating with one another. How far out do you think that is?
A swarm of bots? I don't know. I mean, with a lot of these things, if there's a compelling enough economic reason, I tend to think that it's technically feasible, right? There's not a lot that if we're talking about flying bots, that starts being a big challenge. And
no, that's a natural for mesh network.
yeah. Though again, you have mesh networking has some serious challenges and overheads, and the actual throughput that is achievable once you start meshing starts being a challenge.
How about NFC?
So NFC isn't really a connectivity standard. It's a data transfer standard. It's really used almost exclusively for short range. There are some longer range, but it's really point to point. It requires physical alignment. It doesn't allow for sort of passive data transmission, which makes it a poor choice for IoT devices. Yeah.
On the cellular security, the NSA and all these listeners, are they decrypting or are they getting the voice over the data servers and other?
Yeah, I'm not even going to begin to speculate on how the NSA is taking the data.
So you consider this as being secure?
Well, no, it's that portion of it you don't have to think about. Typically, I wouldn't. It's that you have a proven secure layer there, and maybe that's good enough for you. Maybe that's acceptable. I generally think you probably want to be layering additional security on top of that.
Right. Yeah. Thanks very much. Wow. Everybody's so So just look for our next event. It will be posted soon on our website. We'll try to confirm the speakers. So see you next month. Thank you. And thank you very much for that.
Oh, thank you.
Actually, I got no one.
How do I stop this recording?
Okay. Stop this.
How do you stop recording? Pop right up.
Yeah.
Yeah, sorry, I ran a little long. I tend to talk too much.
It's all right.
Great talk. Thank you.